Section 1.1 is mathematics and problem solving. And the first thing we're going to do is we're going to look at the four-step problem solving process. The mathematician who is sort of credited, if you will, with this is a gentleman named Polya. And so sometimes we'll see this written as Polya's four-step solving process or something like that. I don't usually say this, and usually people don't do it, but occasionally I have someone who will. As we're doing these problem-solving strategies, you don't have to show all four of these steps, but they're usually more of things you work your way through, like mentally. So just be aware of that. I'm not looking like step one and you do this, and step two and you write down that. I'm not looking for that, okay? All right, so the first step in the four-step problem-solving process is to understand the problem. So you might be asking yourself questions like this. Can the problem be stated differently? What is it that I'm supposed to find, or what else is needed? What are the unknowns? What information is obtained from the problem? And what information, if any, is missing or not needed? So you've all had probably those textbooks before. They throw in extra stuff that you don't need, and you get really frustrated because you're like, why did they give me that extra information? Well, the reason that they really do it is because in real life you're given lots of information, and you have to decide, is this useful or valuable information to what I'm working with or not? So it's actually more of a realistic kind of a problem if it has that kind of stuff in it. Your second step is to devise a plan. That is, to think through and decide, how might I tackle this problem? This following list is non-exhaustive. That means there's other things that could be included on here, but it is a list of some really common ones that are used. So looking for a pattern, examining related problems, examining a simpler problem, making a table or a list. Who in here is list makers? It's me. I like lists. They work well for me. Identifying a sub-goal, kind of like, well, if I could just get to this point, I think I could finish the problem. So then you've kind of broken it down into sort of pieces that maybe are more manageable. Diagrams. Anybody here visual? Like to see things on diagrams? That's me too. Diagrams really help me to process information, so that's a really good one. Guess and check, which is really a valid strategy. I know sometimes people are like, that's not allowed, I can't just guess. Well, random guessing is not a good idea. But guess and check is often a valid way to try and figure out something that's a problem-solving, issue. Working backwards. I know you've all used working backwards, and here's how I know it. We've all at some point or another looked in the back of the book and said, well, how did they get to that answer, right? And you work your way backwards from where they came. So working your way backwards is often a very valuable strategy in certain situations. The last one I've got here is write an equation. While I'm not going to tell you that you cannot write an equation, I'm not going to emphasize writing an equation on any of our problems. And the reason is because, for the most part, this content that we're going to be working with, number one, they don't need equations. And number two, you can actually access this information. You can use this information at a much lower level than an equation would show up in. And equations don't show up till middle school, right? Mostly. I mean, you might see something very simple at high elementary, but most of these problems are very accessible even to second grade, third grade, and the equations aren't going to make any sense at that point. So we're going to steer away from equations for the most part. After you have decided how you want to solve the problem, you're going to actually solve it that way. You're going to carry out the plan. So you're going to implement the strategies from step 2, perform any actions or computations that are necessary, attend to precision in language and the mathematics used. Be careful that you're actually looking at what they're asking you to do. I asked my son this morning, what time is the game you're going to tonight? And he said 2:30 on Sunday. It's like, you didn't listen to my whole question, okay? So be careful you read the question thoroughly and understand what they're asking you for. Check each step of the plan along the way, either formally or intuitively. So formally means something like you're checking to make sure your mathematics actually computed correctly. Intuitively is where you ask yourself, does this make sense? Do you understand the difference? Okay. Keep an accurate record of all your work. Showing your work is a really good thing, not just for me to be able to give you partial credit, but for you to be able to look back and say, oh, look, I went wrong right here, and now I can fix it without reworking the entire problem. Okay? And the last thing is to actually check your work. So either physically plug some numbers back into something and make sure it works, or to, again, intuitively decide, does this make sense? So we had, a question about babies, and you tell me that the number of babies is 4.7. I'm going to be like, really? Where are you getting that 4.7 baby? I mean, like, that's crazy, right? So you need to make sure that what you're saying makes sense. Okay, so what we're going to do is we're going to solve some problems. Gauss was a mathematician, very bright, obviously, in early grade school. I believe it's first grade, may have been second. The teacher gave the class an assignment intending them to take them a long time. She asked them to find the sum of the numbers from 1 to 100. So she was expecting them to do something like 1 plus 2, and then take that and do plus 3, and take that and do plus 4, and that should take a while, right? I know you guys are never going to do that when you're teaching. But Gauss's teacher did. Unfortunately, Gauss answered, well, unfortunately for the teacher, Gauss answered almost immediately. He knew how to do the problem. So I'm going to show you the strategy that he used. It's going to be much more formal than the way he probably did it, because it'll help you in creating the same kind of thing for the future. So what you're supposed to be doing is you're supposed to be finding the numbers that are 1 plus 2 plus 3 all the way up to 98 plus 99 plus 100. Right, this is what we're supposed to be adding together. And we're going to call this S. S stands for sum. That's all. Okay, so here's what Gauss noticed. He noticed that if you added the first number and the last number together, what happens when you add 1 and 100? You get 101. What happens if you add the second number and the second to last number together? You get 101. What happens when you add the third and the third to last number together? You get 101. Okay? So I'm going to write this out in reverse order. So S is still equal to what I'm writing down, but I'm going to write it backwards. So this is 100 plus 99 plus 98 plus all the way down to 3 and 2 and 1. And we're going to add this together sort of like elementary style where you add it from the top down. So if you add S plus S, you get 2S, right? 101 and 101 and 101 all of these 101s.
This was a smart little kid.
It was. Yeah, he has done a lot more than just this, obviously. As he grew up, he did a lot of very interesting things in mathematics. So, got a bunch of 101s. But somewhere along the way, you learned a shortcut to adding the same number together multiple times. What did you do? Multiply, right? You multiply. So if you added this together that number of times, you could do that with multiplication instead, but you'd need to know how many times to do it, right? The question is, how many of these are there? That is, how many terms are there?
100.
There are 100 terms. How do you know there are 100 terms?
Because you're adding 1.
Right. So we started with 1 and we ended with 100, right? So there's 100 terms. So let's pause for a second and just ask ourselves, what if we started at 5 instead? We went from 5 to 100.
95.
Would we have 95? Would we have 94? Would we have 96? How did we get 95? I think what we did is we did 100 minus 5, right? But let's think about if you wrote them out. If you wrote out the numbers 1, 2, 3, 4, 5, 6, 7, all the way up to 100, there'd be 100 of them, yeah? But then you threw away the number 1, the number 2,
So
the number 3,
96 terms.
and the number 4. There's 96 terms. You have to subtract how many you took away, and you only took away 4 of them. So you don't subtract off 5, you actually subtract off 4. So just one of those strategies to think about of how do I count terms. They don't always start at 1. Okay, so you have to be careful on how you're counting. We'll have another example of this in a minute. There's 100 terms here. So what did he do? Well, he has this now as the number 101 100 times with multiplication. So then what is 100 times 101?
10,100.
Good, 10,100. Now, this is twice as much as we needed because we added it to itself, right? That's why it says 2s over there on the left-hand side, is we doubled our value by adding it to itself. So to compensate, we now need to divide by that too. And we end up with 5,050. Okay, so that's Gauss's problem-solving strategy of looking for a pattern. This is an example of patterns. He noticed the pattern that if you added the first number and the last number together, the second number and the second to last number and so forth, they all added up to the same thing. That's the pattern that he noticed. Right? If he'd added them in order, he would have never noticed that particular pattern, but he added them out of order. So, what we're going to do next is we're going to examine a related problem. That is, this problem is related to the one we just did, right? And you guys do this problem-solving strategy all the time. It's what happens when you look back for an example in your book that looks like the one you're working with, right? That's what it is. So we're going to find the sum from 36 to 147. We're going to do it the same way that Gauss did it, though. Okay? So we're going to write down S equals 36 plus 37 plus all the way up to 146 and 147. And we're going to add it to itself. Because again, the first and the last, the second and the second to last, it's this pattern. It works the same way all the time. So S equals 147 plus 146 plus all the way down to 37 and 36. All right, so I've got 2S on the left. What do each of these pairs add up to? Yeah, they're 183. And then this goes back to the question I was posing before. How many of them are there? $112. How'd you get 112, Leah?
I subtract 35 from 147 because they started with 36.
Right. So we don't want to subtract 36 because we have the 36th term, right? So we subtract off the first 35. So if you take 147 minus 35, you get 112. So there are 112 terms. So we're going to take the 183, which is the sum of each individual pair, times 112, because there are 112 terms, and we'll multiply them. So what is 183 times 112?
20,496.
And then what's the last thing we would need to do? Right, and where did that 2 come from again? It's adding it to itself, right? We doubled our sum when we added the numbers back to themselves. So this ends up being 10,248. All right, let's actually pause for a second and consider something else. I don't have an example on this, but there is an example in your book that's going to come up. This was really friendly in the sense that every number went in order. There were no skipped numbers. 1, 2, 3, 4, 5, 7, 6, 7. It went all the way up. What if you skipped numbers? What if it was every other number? What if it went 2, 4, 6, 8, 10? What if it went 3, 6, 9? What if it did those things and it didn't even start at the beginning? Does this problem-solving strategy still fit?
Yes.
It does, but we're going to need to alter it some, right?
Would you find the number like we did with that 112 and divide it by 2?
It's a very good plan, yes. So you have to be careful. You want to make sure, like let's say for instance, just for clarity, that it really starts at, like let's just do evens, so 2, 4, 6 all the way up to 100. So 2 up to 100. Well, if I had from 1 up to 100, it'd be 100 terms, right? But I don't have all of them, I have half of them. So I would divide by 2. Same thing if I went from 3 up to, I'm going to say 99 since it ends there, right? I'd have 99 terms and I'd have only a third of them because it'd be every third term. You guys with me on that? So that's not the dividing by the 2 on the left that's happening there. That's dividing by the fact that it's skipping terms that I'm talking about there. Okay, so that's cool. But what if it did both? What if it skipped the terms like that and it didn't start at the beginning? That's trickier. And here's why. Let me give you an example. Just some numbers, that is. Let's say we had this one. 5, 7, 9 up to 53. Well, it's obviously every other number, so we're going to divide by 2. I mean, I get that. That's fine. But the problem is if you take 53 minus 4, 4 would be the number before 5, you will get something that's not an even number. If you divide it by 2, it will be a fraction or a decimal. So that can't be quite right. So when we were looking at the one like Leah did before, where she just subtracted off the number in front, 35, you have to subtract off the number in front that's a part of the pattern. What would the number in front of 5 be if it were going with this pattern? It'd be 3. Are you guys with me? It's the number that's in the pattern that's before it, not just the number directly before. It's a pattern. So the number we would be looking at if we were looking for how many are in this particular sequence of numbers would be that we would do the 53 minus 3 and then divide by 2 because we have every other number, and we'd end up with how many terms? 50 over 2, which is 25. We'd have 25 terms. There are 25 terms from 5 to 53. You have to consider the pattern that you're working with, not just, oh, I'm just looking at the number right before it. Okay? And we're going to stop there because I think that's a good spot anyway.